So I was just testing Drune's foils, so hopefully it should work well. Now this is the second presentation today. This time I'm going to talk about NUMA support, especially in the guest side. And we have two sessions, and I'm going to talk about general enabling part. And he's going to talk about more optimization and advanced NUMA support. Okay, and the title says PB and HBM, but we are trying to combine as much as possible. That's a goal, and I think we had a couple of discussion, and we reached agreement. So that should work. So we have a small Zen community working on guest NUMA support, and we have Andre from MD, and Darun from Georgia Tech, and you guys are very welcome to join us. And again, the goal is not just the HBM or PB, because the major difference is, after all, we have ACPI or not. So that's basically only the difference. So in terms of, for example, the config option, we should be able to use the same identical, same configuration. And Darun is kind of working on optimization, advanced NUMA features. And whatever we get, something like enlightenments or optimization should be applicable to both HBM and NUMA. Okay. Anyway, so this is kind of scope of NUMA project. Okay. This is agenda, and so I'm going to talk about what the NUMA machines are, and importance about NUMA characteristics. You need to understand the different things happen on a NUMA machine. So, and the motivation, and guest configuration, and the current status. And again, Darun is going to talk about more advanced optimization things after this. Okay. So first of all, NUMA machines. This is the one we introduced very recently. So this is not just a theoretical machine. This is a real machine. This is a product. Okay. So this time I use this one. Should work. Okay, good. So you have the node here. Okay. Some physical things, sometimes people call socket. Socket means a physical thing, and from logical point of view, logical point of view, we call this as a node. Okay, and some implementation, for example, a socket has multiple nodes inside. Okay. In this picture, the socket and the node are basically same. Okay. And within the node, socket, we have the cores. Typically, you have a 4 or 8, or can be more. Okay, the cores. And the memory are attached to each node. Okay, and this is a memory buffer, and this is a memory. And notice the DIMMs are scattered all the nodes. Okay, and the orange stuff is basically the I/O hub, and under the I/O hub, we typically have devices, PCI Express 2 devices, like a network or HBA. Notice this, for example, the links are, this has two links, okay, connected to just the two of them, okay. So you can imagine when you go to, if you have a DMF from this node to, something like a device from, beneath this one, below this one, you need to go through this kind of path, okay. So there are some distance depending on, where the I/O devices sits, okay. That's also a NUMA implication too, okay. Now, this is a typical NUMA, and we have more variations. And for example, the one that in the previous page, it's probably something like this, this one. But you can combine using simple building blocks. So today, for example, you can easily build a 8-socket system. Okay. The point here is, you have a various NUMA systems, and they are coming. Okay. This is a foil from Andre, and I have his permission, from AMD. And this was the data was taken on AMD systems, and this is not about the guest NUMA support, but just trying to show how important the NUMA awareness is. Okay. What he did was use Zen, and Zen has a boot flag for the hypervisor, NUMA on, NUMA off. Okay, NUMA on means NUMA aware, NUMA off disable NUMA support. Okay, and he ran the guests, 1, 7, this kind of many guests. Okay, and also so this vertical side means the number of guests. Okay, and he ran 2 benchmarks. One is LM bench. Okay, just to read, and the other one is a kernel build. Okay. One thing we should notice is that this is average performance. In this case, higher is the beta. Okay, so if NUMA is off and you have, for example, if you have a 7, and this is the performance relative to the native, then immediately the performance, average performance, goes down, right? In case of NUMA on, if the Zen knows about NUMA, then even you have 7 gas, it's kind of same, basically same as a native. Okay, so this basically, shows that how NUMA awareness, you really need to have NUMA support in the hypervisor. Same thing with the kernel build, right? In case of a kernel build, lower is the beta, so this is the opposite, right? So as you see the average, if you have a NUMA off, NUMA disabled, you have a higher number, means slower, okay? So, and that trend is consistent. So this is telling that NUMA support is required in Zen, and also telling that the impact of NUMA characteristics, okay? And then that's our motivation. So number one motivation is, as I showed, the more NUMA machines are coming in the market. And actually, in the past, NUMA machines are very high-end. It's very expensive, and you guys don't touch those. But recently, NUMA machines are kind of commodity. So you guys gonna see more NUMA machines. But one kind of thing is, NUMA machine doesn't mean you really need to have a NUMA support, but by the way, okay, some NUMA machines, even small, in a small, small NUMA machine typically has interleaf mode or NUMA mode. So you can, for example, disable NUMA mode to show, to show like a big SMP support. Okay, so, but even in that case, as I show, you're gonna see more NUMA machines, and that's gonna happen anyway. And also, we are hearing that the request, people, for example, HPC area, people wants to run big, very big gas. And memory, for example, as you saw, that the DIMMs are scattered across the nodes, and they really want to use all the memory, okay? As long as you just use a memory attached to a single node, the amount of memory is limited. Also, the number of processors, you want to use more CPUs across the node, okay, and I/O. And kind of good news is, if you look at existing operating systems today, Windows or Linux, they have a NUMA support. So if we run them with NUMA enabled, basically NUMA enabled means we populate ACPI, SRAT, SRIT table, then the OS gonna detect the NUMA and enable NUMA. Once you do that, typically application uses NUMA specific libraries. So key enterprise applications gonna use those libraries to optimize, the application, and so we will get optimization from the guest kernel and also key applications. And in virtualization, this may be kind of a research topic, but there may be some virtualization specific NUMA optimization enlightenments should be available. So that might be interesting, okay? So how do you achieve performance, NUMA performance? The key is you need to understand that basically that memory latency, okay? So in this picture, for example, when you access the local memory from this core, right, you have, it's much closer and the latency is lower. Then if you access, for example, memory here, you have a higher latency, right? So from OS point of view, it needs to know basically two things. One is the first one, right? What kind of memory blocks are there, and also how the processors are connected to those memory blocks, and also the distance from there, right? So in this picture, you have 4 blocks, right? And this SRAT table basically describes that this kind of topology, and the SRAT table describes the distance, okay, local or remote, memory block. And in virtualization, you have to do additional things. First of all, this is I just talked about how the operating system's gonna detect NUMA and set up the memory subsystem and schedule things. Now in virtualization, especially at this point then, what we need to do is bind the vCPU to the node, okay? Because once OS set up the memory initialized subsystem, and then it knows about basically the memory distance, right? Distance to the memory blocks. So you don't want to change that assumption in the OS. And also, when you construct this table, you need to reflect that real platform information, configuration in the table. Otherwise, you probably not, you're not getting optimal performance from the guest OS. The other thing is, NUMA is kind of a necessary evil. People really want to avoid to have NUMA. But if we really need to support NUMA, what people typically ask for is predictability and also repeatability. They want to, for example, get the same performance, same behavior every time they run the NUMA system application. And this is, in virtualization, actually that's even harder, right? It's more complex because you have other guests running. And so that should be, challenge anyway. Okay. So how can we construct SRAT and SRAT for the guest? Now we have today in Zen we have a so-called host NUMA API. Those the API essentially gets the information equivalent to SRAT or SRAT. Well, in other words, those were invented to construct SRAT and SRAT for the guest. Okay, so we have two parameters for the hypercall. So one is get the number of socket cores, the hierarchy information, and the other one is basically get the memory block information and the latency. So combined, with these, we can construct guest SRAT and SRAT. Okay, then we propagate that SCPI table to guest. So in this case, for example, you have if you want to have a 2-node NUMA system, right, and uses some amount of memory here, right, and here. In this case, SRAT basically talks about, this is your memory, okay, 2 blocks, okay, and SRAT is gonna tell the distance here and this one, okay. This is the NUMA gets gonna see, okay. So it's not gonna see the entire view, basically just a subset, but still reflecting hardware condition characteristics, okay. Then we have a memory allocation strategy, so-called confined split. I'll have more details on the next page, okay. Before going to the memory strategy, I just talk about how we can set the number of nodes, okay. Just one thing is the number of nodes doesn't necessarily mean the number of the nodes that the guest is seeing. It just means how many nodes from which the memory is allocated, okay. And this is the minimum guess and the maximum guess is idea from Andre. And maximum guess specify the maximum guess you want to see, okay. So it's the maximum value is obviously the number of system node, okay. And minimum guess node is the minimum number. And if the allocation fails, okay, you're gonna see failure, okay. and by default it's 1. So if we, for example, set minimum like, say, 2, right? And maximum is, for example, 4. If you do that, you don't know how many nodes you get, okay? But at least you will get the two memory will be allocated from 2 nodes at least, okay? And depending on the memory allocation strategy, the number of node will be shown to the guest or not. Okay, I'll have a more detail on the next. Okay. So, and if you really want to have a very fixed, static configuration, let's say you really want 4 nodes, and you want to the number to be exposed to the guest, then you set minimum is 4, and also maximum is 4. Okay, if you do that, you always get the same number of nodes and visible. Okay. So this is a memory configuration. So we have at this point we have 4. Okay, but the last one is combination. So essentially we have 3 of them. And the 2 nodes then, okay, if we use 2 nodes, either 2 nodes then meaning confine or stripe case, guest is not the NUMA, okay. So for example, the confine case, you allocate the memory from just 1 node, so it doesn't make sense to tell you have 2 nodes, right? So just 1 node. Likewise, stripe case, it's using interleaving to get the memory. In this case, also we don't expose the number of nodes to guest or even construct the SRAT. Okay. So for this case, we essentially have a big SMP. Okay. Then the split case, you allocate memory equally from each node. So if you say 16 gig and 4 nodes, then in that case you allocate 4 gig from each node. Okay, split equally. Okay, that's a split. Now, if you specify memory allocation and the memory you cannot get that kind of memory, then it fails. You see the failure. Okay. Oftentimes you don't want to see guest creation failure. In that case, you can try automatic. And in that case, the memory allocation try to do the best effort to get the memory. And in that case, you don't know what kind of memory layout you'll get. Okay, but this is the most flexible configuration. Okay. Again, so it's a little bit. It's not complex, but Drew will be repeating this, so don't worry about at this point. So now we're done with the configuration, and I remember that Dan raised that live migration things, and this is we haven't done completed live migration support. Obviously, that's much harder than just supporting a typical gas. And then I just talk about the the live migration. So at the time of migration, first of all, we need to make sure the number of nodes must be same, right? Especially split case. And because from a guest point of view, you don't want to see different nodes upon live migration. It's very hard to reinitialize that OS data structure when you change that number of nodes. So you don't want to do that. And if you use particular memory allocation strategy, at this point, I think we should use the same memory strategy. So let's say, for example, if we use confine, then confine on the target. So once you get the memory from the destination, from one node, right, then you can make sure, at least from memory point of view, you can do byte migration. Likewise, a split case, if you create a guest with a split, right, then find the nodes on the target destination. Then if you are sure you can get the memory using a split, then you can do migration, okay? And as long as the target, the destination, has similar NUMA characteristic, we can expect that the guest will run almost, in a similar fashion, the same mean, same performance, okay? Assuming the process are also same, okay? So this is just I'm almost closing at the current status and next step. So we have the host NUMA API. I told, right, to get the number of nodes and socket and core, and also the other one is memory distance and the block information, basically equivalent to SRAT and SRIT. It's already there, okay. And we already, internally we have patches, and we at this point are rebasing to the latest upstream and measuring performance. We got a good result, but we are not comfortable with telling the performance at this point. So now also working with Andre and Drew to merge the patches so that we can submit the patches to the upstream. And next step is performance analysis, run different workload. We are very interested in running a big workload like a database, enterprise workload like Oracle. So, and I heard, some people are interested in NUMA scheduling optimization. So we look at the scheduling issue. At this point, we need to bind the VCP to node. Okay. We may want to kind of relax that the condition. The other thing is IO NUMA. Remember, even this one is. You see, this orange stuff is IO hub, right? I talked about. So when you do IO, for example, you have a nickel around here, right, below this IO hub. Then if you do DMA from DMA to this node or that node, you may see different performance. We don't know, okay? We don't have a data. So that's the things we want to look at, okay? And combined with a direct IO assignment, okay? That has impact on, for example, IO TLB things, okay? So that's very interesting kind of analysis. The other thing is live migration. So if anybody interested in a live migration, you are welcome to take it. So, and this is, I think, end of my presentation. Any question? Maybe we can take a question after the maybe. So.
So the question I have is, do the patches also do vCPU pinning? Do they also do pinning of the guess to the correct CPU?
I couldn't hear. Sorry.
So actually, okay. Do those patches actually also do pinning?
Oh, okay. It does, yeah.
Okay.
So you can use this one? No, it's already there.
Okay, one more question.
Hey, June. In your pictures there, it looked like you were showing node with local memory, and then you had 2 levels of memory. You meaning in your picture, it looked like I wasn't quite sure what you. Okay.
The memory buffer.
Okay, so
it's
that.
Not really 2 level, but we're kind of doing buffering.
All right.
Yeah.
So basically, each node has local memory.
Local memory. Yeah, the DIMMs are attached to each node.
To the node, okay.
Right.
I worked on other NUMA architectures where you have some local memory per node, and then there's global memory, which is equal distance from each node. So I guess in a scenario like that, whatever you guys have done, would that work in a situation like that?
Well, I don't know. These are the picture I showed were basically the NUMA system we have today and coming. So if AMD has same thing, that's probably the ones we are interested in. So I don't know what kind of a NUMA system you're talking about.
Yes, an IBM.
It's based on x86.
PowerPC.
Yeah, so it's probably different. Yeah, we can talk offline. So you can use this one.
Okay, any other questions? Okay, and actually now we are a bit short on time. You guys already used 30 minutes, but let's try to make it quick.
You also have this one.
So I'm going to talk about the motivation, and I'll just briefly revisit the motivation for continuity, and then the memory allocation strategies, the allocation scheme, PV NUMA guess, and the summary. That's the agenda. So in the motivation, it's basically like showing that the remote node axes have a high overhead. Even for a small NUMA machine like the one I have, which is a 2-node Nehalem machine with 6 GB on each of the nodes, and cores like 0 to 7 on one node and 8 to 15 on the other one. Even on such a small machine, we have considerable non-significant overheads in accessing remote node memory. So obviously this shows the overheads with the worst case overheads with the modified cache coherency states. But even with other cache coherency state tests, which were exclusive and shared, the trend is similar. So, okay, so part of the motivation is, as Jun already mentioned, we want to reuse a number of optimizations that the modern OSs already have, Linux, Windows, or any other OS for that matter. Linux in particular also has a multiple NUMA allocation policies which are exported to the applications, and the applications can use these policies to for their specific application requirements too. And this is about so this provides significant performance improvement through system level NUMA optimizations. And there are entire range of applications which also benefit directly from using specific NUMA policies that they are interested in, and those are exported through NUMA CTL libraries. And so basically the conclusion, skimming through the entire thing, and conclusion is there are a huge number of NUMA-related optimizations in the modern OSS, and there are way too many of them to be just discarded. So now coming back to the implementation on Zen. So Zen currently uses kind of ad hoc and minimum effort memory allocation as it is right now. So what it tries to do is it tries to allocate all the memory from a single node and pin all the vCPUs to the node, and done. So this is not always possible to do. For instance, when the VM itself cannot fit into any single node, this is not possible to do. And there are other cases like after a few VM allocations, it is possible that the free memory, the node free memory, is fragmented across, and we might not be able to find a single node which can fit in the VM. And that's not just the end of the problems. So with memory over-provisioning, such as ballooning features, it is still possible that even though we allocated all the VM memory from a single node, after a set of ballooning operations to increase and decrease the reservation, etc., we might end up with pages from all over again. But I have everything, actually, it's fine.
It's fine?
Yeah, it should be fine. I think it's okay.
It's okay?
So we'll keep revisiting this table, and as the first row mentions, right now, when if I try to start an 8 GB VM on the machine that I mentioned, most of its memory, in this particular scenario, comes from the physical node 1. But as it happens, the code somehow manages to pin it to the wrong node. So it is just to show that there's a lot of scope for improvement in what we are doing right now. So coming back to the VM memory allocation strategies that June has already introduced. So first one is the confined strategy, in which we try to allocate all the VM memory from a single node. And the obvious goal over here is to maximize the performance. And the second strategy is the split strategy, where we try to split the VM memory equally across a set of selected physical nodes. And then also enlighten the guest or inform the guest of this topology, either using the ACPI tables or using the enlightenment in case of PV. And the goal, again, is to maximize the performance. The third case is the striped allocation strategy, in which we interleave the VM memory across a selected set of nodes again. But the goal over here is to rather provide some kind of average but predictable performance. We'll go back to the results in each of the cases and see how this works. So again, in picture, it says the same thing, that VM memory is allocated from a single node in case of confined, and then it just constructs a one-to-one mapping between the virtual node and the physical node. And one might wonder, why do we need enlightenment in the case of the confined thing? it goes back to the memory or provisioning thing that I was talking about, that with ballooning and other features, we benefit from having this one-to-one mapping and in order to keep the strict mapping, basically. So in the split strategy, we split the memory equally across, from a selected set of physical nodes. And then, so we basically distribute the domain memory across a set of V nodes. And then we distribute the vCPUs across these V nodes equally. And then we enlighten the guest so that it can internally construct its virtual nodes and start working. And finally, the stripe allocation strategy, we interleave the memory allocation in the specified stripe size across a set of nodes. And the vCPUs over here are pinned to the logical sum of these nodes. So if the VM memory comes from like say 3 nodes, all the vCPUs of the VM are pinned to these 3 nodes. So those were the allocation strategies. So as Jun already mentioned, if a configuration file specifies the strategy that it wants to use, and we are not able to fulfill that, the allocation fails. But in the default case, we need an automatic allocation scheme, and this is that. So we first try to confine the VM to a single node using a best fit decreasing heuristic. Then we try to allocate. If that fails, we try to allocate using split strategy, again using best fit decreasing strategy. And over here, what we can do is so with PV, we have a benefit that we can figure out if the guest supports NUMA or not, or if the guest has NUMA enabled or not. And this is done by adding an ELF node. So the ELF node is used as a hint to see whether it makes any sense to use a split strategy or not. So, and if we fail doing even the split thing, we fall back to the striped. And over here, we are using the fast fit increasing strategy, which I'll describe later, which tries to, the goal of which is to reduce the fragmentation of the free node memory. So as mentioned here, the best fit decreasing always returns the minimal subset of the nodes and tries to pack up the nodes as much as possible, trying to reduce fragmentation. And FFI allocates in the reverse order. That is, it tries to pack up the nodes as it goes along, but it might end up allocating memory from more number of nodes, and it tries to find the maximal subset. The main idea behind this was, anyway, it's getting some kind of average performance. We might as well reduce the free node fragmentation, free node memory fragmentation. So with the split strategy, we try to construct a strict one-to-one mapping between the virtual nodes and the physical nodes. As mentioned again, so HVM exports this memory layout using the ACPI tables, and the PV exports memory layout using the virtual NUMA enlightenment, which is mentioned next. So a virtual NUMA enlightenment basically looks like this. It just provides the same piece of information that the ACPI tables do, the slit strat tables do, plus just one extra piece of information, which is this V node to M node mapping, which we'll see later, how it is exactly used in the over provisioning features. So there are 2 parts to the PV NUMA guest. One is the construction of the virtual nodes, and the second one is the maintenance of the virtual nodes. In the construction, it's a very simple thing to do. We read the NUMA enlightenment using hypercall, and then we construct the virtual nodes and the CPU to node mappings, etc. internally. This is similar to just faking a set of nodes in software. And finally, so the important thing is the distance between the virtual nodes actually reflects the actual distance between the underlying physical nodes. So still, the guest knows about those characteristics which are important. So coming back to the table, as we can see in the second row, if you are using the enlightened startup, the mapping is, well, perfect. between the virtual node and physical node. And the VNMR is perhaps a badly named metric. It's a virtual node misplacement ratio, which just measures how much the pages have gotten misplaced from the initial startup time. So coming back to the PV NUMA guest and the maintenance of the virtual nodes, so when we use ballooning and the increase, decrease, and the exchange memory reservation operations, those are not NUMA aware. And with such interfaces, we might end up like changing the MFNs like from under the feet of the PFNs and still end up like with a higher VNMR. So one of the changes that I did was to modify these interfaces to use the virtual NUMA enlightenment, and that's the V node to M node mapping that I was talking about previously. And this just keeps the strict mapping between the virtual and physical nodes. And again, as shown here in the table, the third row shows the problem that after a set of ballooning operations, we reached very high VNMR, as much as 50%. And I mean, 50% could be the worst possible thing in the provided setup. But yeah, so and after enlightened ballooning, we still keep the same, we keep the VNMR to 0, basically. So, but there is a problem that it introduces, like as previously pointed by Dan correctly. And so the problem is if we are mixing multiple allocation strategies, which we will obviously end up doing, and VMs which are using the confined and split strategies might just like wait for memory from a certain node, but it might not be available. So it could lead to some kind of starvation for those VMs, although there is memory available in the system overall. So under heavier memory pressure, like we relax the strict one-to-one mapping between the virtual and the physical nodes, and that causes a divergence. But we also provide a mechanism to the guest in order to track these changes, how much of which pages are allocated from the wrong nodes and other stuff. And over a period of time, by sweeping through the memory, the guest tries to converge to an original state. So this is not part of the patches that I already posted, but this is already coded, and we have some results for it. So I don't have an entire range of results here. You can mail me for the results, but yeah, this is from running a LinPack benchmark for a 20,000 by 20,000 kind of workset size, which was a 4 GB workload. And as we show, okay, so the first bar over here is current thing. This is the confined, this is the split, and this is the striped. So as we can see, the current, the numbers with the current allocation thing, there's a huge variation in the performance, and also the average performance is considerably bad. With the confined and split strategies, we get consistent and best performance almost all the time, actually all the time. And with the striped allocation, we get so I was using a stripe size of 1 MB in this, and there are a few more results with 4 KB and varying stripe sizes. But even with the 1 MB stripe size, we get a considerably better predictability in performance and good average performance too. So summaries, we covered the allocation strategies, the automatic allocation scheme, NUMA guess with the split strategy, the HVM, and the PV part 2, HVM using SlitStrat, and the PV using enlightenment. And with the PV NUMA guess, we covered the construction of the virtual nodes and the maintenance of the virtual nodes. That's it.
Okay.
You do mention about allocating memory from certain nodes, but you don't mention anything about vCPUs. Is there a restriction that you have to use all vCPUs in a node if you allocate memory from that node?
So when we allocate memory from a particular node, we try to pin the vCPUs to that node. Is that the question, or are you asking if we are?
Would it be possible to use memory from a node where you do not have any vCPUs?
No, it's not because we pin the vCPUs.
What if you have only 2 vCPUs, but you want to use all the memory in the system, or a large amount of memory.
You have only 2 vCPUs and you want to use all the memory in the system. So you mentioned the memory requirements in the configuration file. And
so if you want to co-locate, for example, a memory-intensive VM and a CPU-intensive VM, you won't be able to split the vCPUs between them.
Can you give me a more specific example? I mean,
let's say you have a memory-intensive database application combined with a very CPU-intensive application server, where the database only needs 2 vCPUs to support the load, but it needs to cache a lot of information in memory. It would be able to use NUMA very effectively, but you're forced to give it all of the vCPUs, as many vCPUs in the system as there are, which means it can interfere with the CPU-intensive application.
so that's why we provide like 2 different options here. One is we use automatic allocation scheme, where we are deciding a bunch of things. And for specific application or the VM requirements, like you mentioned, we export all the strategies that we have, and they can choose from them.
Right, but let's say you do want to use a split strategy. That means you're forced to give that VM as many vCPUs as there are.
So you are trying to say the number of vCPUs is at least as much as the number of vnodes?
Yeah.
Yeah, that's a requirement right now.
Okay. All right, thanks.
Yeah.
When you do the striping, what is the stripe size?
So I was using a stripe size of 1 MB.
Is there a requirement? Is there any?
No, there's no
flexibility there,
requirement.
any
We are
applications?
hoping to keep it as a tunable kind of thing.
So the striped version, you said you were aiming for predictability,
Yeah.
but that was the one with the biggest error bars, wasn't it?
So the first error bar was the current Zen thing.
Yeah, no, but of the other 3, the one on the right was the one that was aimed for predictable performance, and that was the one with the biggest error bars.
It still has like no. So the stripe size that I was using over here in this result was 1 MB, and so it's we cannot. So it reduces the margin, but we cannot ascertain that we'll get really predictable performance all the time. It depends on the application, right? I mean, if there are some really hot pages which happen to be on the remote node all the time, or local node some of the times, it just depends on the pattern of memory access pattern of the applications. But with the 4 KB page size that I tried in other results, I got considerably better predictability. So, so I think it depends on the application memory access pattern and then the stripe size. It will be a